Welcome back to Fat Mama Physics. This video is a continuation of our last video on adding vectors. In this video, we're going to look at how do we add vectors using the component method. So when do we need to use a component method when adding two vectors? I briefly glanced at it in the previous video, but the idea is that if you have two vectors that need to be added, something where you have one vector like this and you add the tip to the other vector like this, and when your resultant vector forms something that is not a right triangle. Okay. This means you cannot use the Pythagoras theorem, you cannot use SOHCAHTOA. So what happens then if you need to find this resultant vector right there, resultant R, and then T I use for total. I'll use that again in the examples. So how do I do that? I'll spare you the reading here, but basically you need to draw the vectors, you need to break down your components, add the components separately, then combine them together. So let's go through each of these steps one by one while dealing with an example. Okay, going straight to an example, an airplane traveling south. So let's, of course, first draw a picture. We have an airplane that's going south at 1,020 kilometers per hour. It experiences a bit of tailwind, so that's like wind blowing from the back, blowing at the back of the plane. It's blowing at 210 kilometers an hour at 23 degrees west of south. Okay, so it's some vector that's going some at an angle in the west-south direction. Okay, we don't know that angle yet, we'll work it out. Okay, so that is 110, and it's not that big compared to 1,020. So 210 kilometers an hour. And then how do you figure out which angle it is? We look at the directions west of south, which means we gotta flip it around. We first go south and then we go west. Okay, so that's the angle. I'm sorry, it's a little bit tiny. Let me fix it. So that concludes our first step, well, partially. Draw the vectors from tip to tail. Notice we've done that again, tip to tail. And then we need to determine which directions are positive. Now, in this question, it may not be so relevant, or it may not be so necessary, but it is very important for other particular questions. So let's do it anyways. What I mean by determining which directions are positive means that when we deal with 2D vectors, we have the x and y axes, and in our case, we only need to deal with the south direction, and we need to deal with the west direction here. So only these two. And because of that, I'm just going to designate them to be our positive direction, meaning that if I have any vectors going north, they will be in a negative direction, or they will, when I add and subtract, they will get a negative value. Okay, so that's that's necessary when we need to add or subtract vectors depending on their direction. Okay, So this example is very simple. We just have vectors adding on top of one another, but then you'll see in example 2 where it's different. Okay, so that's important. I designate south as positive, means north is going to be negative and east is going to be in our negative direction, which we probably won't use in this question, but it's important to do at the beginning of your question. Okay, so next up we need to label the vertical and horizontal x and y components of each vector. So for the y component, I'll use green. And we already, from the plane, this is already going in the south direction. So we don't need to break that one up. That's already going vertical. So we leave it as that. However, our wind has both components, both a y component. So this one over here, I'm just going to label y here. We don't know what it is. And it has an x component, which I'm going to use this color blue for that. So we have x component of the wind, and we don't know what it is. So we labeled it, and now I should have it up here. You need to calculate it. Okay, so you need to calculate it out, otherwise we can't do the next step. Okay, so let's do this particular vector, the wind. So let's start with the y. The y is adjacent to our angle of 23 degrees, and we know the hypotenuse, meaning we're going to use cosine. Okay, so cosine of 23, and if you don't remember, SOHCAHTOA, ka, adjacent, hypotenuse. Okay, so that is our adjacent y over our hypotenuse, 210 kilometers per hour. We solve for the y by multiplying two sides by the 210 and the kilometers per hour I should have there. And we get y is equal to 210 cosine of 23. We put it in our calculator. 210 cosine 23, bam. 193. .3 kilometers per hour, and I'm going to label this south. Okay, next up we have our x component over here. We have the opposite side, so that is, and then also the hypotenuse, so that's sine of 23 equals our x over our, should be two dots there, 210 kilometers an hour, multiply both sides by the 210, and we get x is equal to 210 kilometers an hour sine of 23. And you know what? I'm gonna save this number on my calculator, my previous one, 193. That's my y. I'm gonna store it as alpha y because I'll need it later. Okay, and then now I'm gonna calculate my x component, 210 sine 23, which I'm also gonna save 82.05. I'm gonna store it as alpha x. To be honest, you can store it as any letter. I'm just using it the same letters as we have in the question for our own convenience. So 82.05 kilometers an hour, and this is going west. Going to the west. Okay, and now we have all our components broken up. So we have all our pieces. Now we put the pieces in their own categories. So let's start with the x, since we were just dealing with it. So x, okay, sorry, let me just check this off. We've done that. Now we need to add these components separately to get the total. Okay, so I'm going to use x total for the total x components. And we only have the one, the 82, so that's all we do. That's all we need. 82.05 kilometers per hour. And the reason why I'm writing the dots instead of the rounding off, because I need to use these numbers to calculate something else later. And I don't want to round in middle of a question. Always round at the last step, okay? So that's why I'm saving all the numbers, saving all the digits, just so I have them. Okay, we have our x component, now our y component, our y total. So we do have the two components. We have the one from the airplane. So that's going south, 1020 kilometers per hour. Okay, and we also have the one from the wind, the 193 plus 193.3 kilometers per hour south. The reason why I'm adding them is because they both point in the same direction. That is very important. This is why I told us to label directions at the beginning of the question. So the same direction vectors can add along the one axis, and then the opposite. If, for example, if this plane was traveling north instead, I would actually need to subtract the wind's velocity from that, or actually vice versa, because I labeled as south as positive. But whenever you have opposite facing vectors where you're adding, you need to subtract them. In our case, we're adding them because they're in the same direction. Okay, keep that in mind, what I just said, because you're gonna need it in example 2. Opposites subtract, same directions add. And they must be along the same axes. Okay, so notice all my y vectors are dealt with in their own separate bin. Okay, now let's go back to our calculator, and notice I've saved the y up already. I'm going to recall it. So that's my number. I kept all my digits. I'm going to add 1020 to it. I get 1213, and I'm actually going to store that and rewrite over my y variable because I don't need my old one anymore. So I'm going to save it there as my y total, 1213.3 kilometers per hour. And this I know is going south because both vectors were pointing south. Okay, so now we have the totals, okay? We're done this step. Now, we need to add the total vectors components together by aligning their vectors tip to tail to get a right triangle. So this is exactly like the previous video where you have two vectors. This is exactly like the last video where you put two vectors together, you add them together to get your resultant vector, okay? So this is where you... So this is exactly like the last video where we took two vectors and we added them together tip to tail to form our right triangle. So now after breaking everything down, we've gone back to the basics again. Okay, so let's let's do that. But first we need to draw them out. So let's draw our vector here. We have our y direction going south. So I'm going to draw this here. And our y total is 1213 kilometers per hour. And we have our west component, which is a little bit smaller, this one over here, 82.05 kilometers per hour. And our total is going to be this one here. And I'm going to finally label this as our R total. And notice, if I go back to my previous drawing over here, this would have been this R total over here. Okay, so this R total is the one I would have tried to find. Now, if you do know, say, cosine law, or you know some more advanced mathematics, you could just directly calculate RT. But I prefer you use a component method because it is always reliable, okay? But essentially, these are the R totals. This is what we were trying to find since the beginning. So now we're finally here. And now we have a right triangle, which we can use Pythagoras to figure out our hypotenuse. So let's start here. I have our c squared equals a squared plus b squared. And we have, so I'm going to label this RT now because I'm going to say that's a resultant vector. We have the 1, 2, 1, 3, and I'm kind of getting a little bit lazy. I really want to speed things up. And then our A2.05, and I don't need to, I have them saved on my calculator. I don't need to worry about kind of rewriting everything, but just to make sure we're always using all the digits in our numbers. So let's turn my calculator on. I have them saved. I have alpha and y, so just double check I have all the right numbers. Okay, so these are the numbers I want. So I do alpha x squared plus alpha y squared, and that gets my answer. I take the square root of it, and that gets me 1216. 1216. Yeah. Hmm? 193. Did not get that? Oh, I guess I didn't. I just got some bogus answers. Okay. And now 1.13 squared and that squared. Okay. That's okay. So let me just double check that I have all the right numbers. So that's my y confirmed, my x, that is confirmed as well. I will take the square root of my x squared plus my y value squared, which corresponds to the ones I've written in my notebook. 1216, 1216 point blah 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 kilometers per hour. I'm gonna round this one off to 1200 kilometers per hour, just to check that's 2 sig figs. Yes, because I have 2 over here. Are we done? And yes, you're right, we're not done. Okay, we need to find the angle over here. Let's use orange. We need to find this angle right there. So to get our final directions, we have our angle, we have the adjacent, we have our adjacent, we have our opposite, and we do have our hypotenuse, but I'm just going to use our original numbers there. And adjacent, opposite, that is TOA. So that's tan of our theta, which we don't know, is equal to our opposite, 82.05 over our 1213 kilometers per hour. Okay, and then we need to isolate for theta, so we need to take their inverse tan of 82.05 over 1213 whatever that is. And since we have them all saved on our calculator, we don't need to worry. Our 82 was our x, so I'm going to do second tan alpha x divided by alpha y, which is our larger number, giving us 3.868. 3.868. And I'm going to round that to 2 sig figs, 3.9 degrees. And to find our final language here, we're going south and then west. So I'm going to say west of south. Because it's always the flip of what you think it is. So here we are. We have one. So this is using component method when we add 2 vectors together that don't form a perfect right triangle. Okay. So quick recap. Draw a picture, labeling your directions, breaking all your vectors into their components, add the components up all separately, put the totals together in the form of a right triangle, use Pythagoras trigonometry to find your resultant vector, both magnitude and direction. Okay, so I'm going to give you a chance to try this out yourself with example 2. And don't forget, if the 2 vectors oppose each other along the same axes, you must subtract them. Okay, so you have an airplane heading 67 degrees north of east, flying at a certain velocity, but this time it's going to experience some headwind, okay, something going against the plane. That's blowing directly south. Calculate the plane's resultant velocity. Okay, so good time to pause the video. We will go through the question afterwards. Good luck. So we got our plane going north of east. At that angle, we add the wind, tip to tail, it's going south, and the resultant velocity is such. Our labeling our directions: north positive, east positive, and south in the opposite directions negative. Breaking our components of our plane down to x and y at 67 degrees in north of east. So that's the adjacent side, so that means we're using cosine to find the adjacent side, which is the x component. And that's going to give us 386, and I just saved it on my calculator for all the digits. No rounding until the last step. Okay, so then now we have the opposite side, so we use sine to find our y component of our plane. It's a velocity, and that gives us 909. And saving that on a calculator again so that we have it for later. So now we can add our components together in the x and then the y. So the x direction, that's only our plane. But now notice in the y direction, our wind is opposing the plane's velocity going south. So that's why we subtract it from the plane's velocity going north, giving us 749 kilometers per hour north. And now we're putting these the totals together in a right triangle, and to find a resultant velocity. So using Pythagoras theorem, we can find the hypotenuse, giving us our resultant velocity. and putting that in a calculator. You notice I used my saved values as 840 kilometers per hour. That's rounded. Don't forget the directions. So as our angle, opposite and adjacent gives our tangent theta. And again, I'm using my saved values, which is very convenient, 63 degrees. Since I go east and north, so reverse giving us north of east. Okay, so here we have the solutions here. Now, notice that the plane is traveling at a little bit lower of a velocity than it did before because it's experiencing it's getting some headwind, which is slowing it down. And because of that, notice we also had to subtract the vectors along the vertical line because we had south and north opposing each other. And as a result, we get this final resultant vector, which is a little bit it's not going as north, but it's still going in a relatively eastward direction. So here we have our final solution here. So hopefully this was helpful for you, that you can rewatch it and use these examples to help you with your problems and examples. So thank you for bearing with me with this video. Good luck, and I'll see you next time on Fat Mama Physics. Signing out.